In this video, we'll talk about the gravitational attraction force, or as this is sometimes referred to as Newton's universal law of gravitation, which says that all masses are attracted to each other. They have a gravitational attraction force between them. And the magnitude of this gravitational attraction force, which is the same for both objects. So let's say I have, this is mass 1, this is mass 2. They both feel exactly the same force acting on them, and it's an attractive force. So this little mass attracts the larger mass towards it, and the bigger mass attracts the smaller mass towards it. And the magnitude of this gravitational attraction force, Fg, is equal to capital G times the product of the masses, m1, m2, divided by the distance between them squared. So r is the distance between them here. And the reason that it's an r, maybe these are planets, so one is orbiting around the other, or they're orbiting around each other. So this really becomes like an orbital radius, and I think that's why r is used for this. But r is the distance from center to center of the two objects. It's not the distance between them and half that, it's the distance between them. Because if it were to orbit around it, then the entire orbital diameter would be twice that. So it's just this orbital radius. And m1 and m2, these would be the two masses. So let's say this is mass 1, this is mass 2. So it's directly proportional to the product of the masses, inversely proportional to the distance between them squared. And then the constant of proportionality is what we call this gravitational constant. So this capital G is the gravitational constant. It is a capital G. And this is found actually experimentally. This gravitational constant it's not a theoretical value, it's actually a experimental value. And the way that it's found, this little experiment here, there's two masses. There's a mass here, same mass here, and then there's little masses placed on a rod, which is connected to like this, it's quartz fiber rod. So they're on a rod that's connected to another rod here that has a mirror attached to it. And when these balls are placed on here, these masses are placed on here, there's a gravitational attraction force between them. And this mass attracts this one this way, this one attracts this one this way, and they cause this rod to rotate around. And then knowing the properties of the rod and using a light to hit this mirror, we can see how the angle changes. So we know how much the rod rotated, and we can say how much force was generated by placing these masses next to each other to get this rod to rotate. So this is how we can experimentally find the gravitational constant, and this value is given in your textbook. This value of G is equal to 6.674 times 10 to the negative 11th. And the units here are Newton, because we have to get gravitational force must be in newtons. So this is Newton meters squared per kilogram squared. So this is the gravitational constant G, which goes into the gravitational force equation here. Okay, so this is the gravitational force, or Newton's universal law of gravitation. Some of we see some of the effects of this. The Earth pulls on the moon. This is why the moon goes around the Earth. The moon orbits the Earth, so it's going around in a more or less a circle, and so it must have some centripetal acceleration, and therefore it must have some centripetal force. We talked about this previously, and so our centripetal force here is the gravitational force between the Earth and the moon, which is equal to, this is G times the gravitational constant times the mass of the Earth times the mass of the moon divided by the distance between them. So I guess the distance from the center of the Earth to the moon. We'll call this radius Earth to moon squared. And that would be the gravitational force that keeps the moon moving in a circle. Of course, then the Earth, or the moon, pulls back, and there's liquid on the Earth, we call water, that moves because the moon can pull it there, and this is the reason we get tides. So as the moon is moving around the Earth, let's quickly run through these. We have the sun pulls on the Earth, and that's what causes the Earth to go in orbit around the sun, or keeps it in orbit. Otherwise, the Earth would fly off in a straight line. It pulls it towards the sun, also pulls the water on the surface, and then the moon pulls it as well, and this is when we get a spring tide. So this is, I can show it better in this picture. If we had the sun over here as well, so here's the sun pulling on the water as well, then we have the sun pulling on it, we have the moon pulling on it, and it makes a very large bulge over here of water, large bulge over here as well, and then very small amount here. So we have low tides on the edges here and high tides out here. This is what we call a spring tide. So we get spring tides when the moon and the sun are in line. So spring tides here, and when they're out of phase, if we have the moon down here and the sun over here, then the moon is pulling the water this way, sun's pulling it that way, and we get this neap tide, which is a lot smaller than a spring tide. So that's the reasons for the tides here. Also, another interesting thing, black holes. The idea of a black hole is that as something gets more massive, right? If we have a more massive planet, then it has a larger gravitational force, and when it gets a larger gravitational force, it can pull more stuff in, and it continues going and going and going, and pulls more and more stuff in, and getting stronger and stronger, and eventually it gets to a point where the gravitational force is so strong that even light can't escape it, so it pulls everything in. This is the concept of a black hole. Also, astronauts far from any planets, you see here the gravitational force is equal to gravitational constant times the product of the masses divided by the distance between them squared. If you just if you double the distance, if r goes to 2r, then you've quartered the force, right? Because this would be gravitational force would be g times m1 m2 divided by 2r squared, which would be g m1 m2 over 4r squared. So doubling the distance makes it 1/4 the force. So it falls off very quickly. The gravitational force falls off very quickly. So if you move away from any stars or planets, any other masses, you go a long distance away, then the gravitational force becomes very weak. It doesn't become zero, it just becomes very weak, and things feel much lighter there.